All right, good morning or good afternoon, AP Calculus, depending on what period you're watching this video or whenever you're watching it. Tuesday, March 3rd, we're looking at Chapter 4, Section 2, something called the mean value theorem. And today's lesson is going to have two parts to it. The first part, we're going to look at something that actually comes before the mean value theorem, a specialty thing that happens before the mean value theorem, and we will look at an application of it. And then we will look at the mean value theorem in earnest and an application of the mean value theorem, at least one application of the mean value theorem. All right, here we go. So first, before we actually do the mean value theorem, I want to do something called Raleighs Theorem. R-O-L-L-E'(S) theorem. Raleighs Theorem. Now, Raleighs Theorem is kind of a special case. It kind of happens before the mean value theorem. It's a special case of the mean value theorem. And if we understand Raleighs Theorem, I think it makes the mean value theorem a little easier to understand. And what I'd like to do is, first I want to give you just the theorem, write the theorem down. Very difficult to kind of understand just by looking at the theorem itself. But then we'll draw some diagrams and kind of rip the thing apart and say, well, what does this mean and what does that mean? So in Raleigh's theorem starts with let f, some function f, be a function that satisfies the following conditions. Be a function that satisfies the following. So f is some sort of function that satisfies the following conditions. First, f is continuous on a closed interval. F is continuous on some closed interval from A to B. No discontinuities, no asymptotes, no holes, no jumps, nothing like that. Nothing weird going on there. 2, the second condition. F is differentiable on, and here we're actually interested in the open interval from A to B. So notice the parentheses. So it might not be differentiable at the endpoints. Can you think of something that might be a function and might be continuous but not differentiable at the endpoints? Think about like a semicircle, and a semicircle is continuous but at the endpoint not differentiable. And the third condition is that f of A is equal to f of B. All right, well, what does that mean? Well, that means that the value of the function at one endpoint is the same as the value of the function at the other endpoint. Now, if you can't quite see that, that's okay. We're going to draw a diagram about this in a moment, and we'll take a closer look at it. But what's the conclusion here to Raleigh's theorem? If these things are true, then there exists some number, number C that's in the interval, open interval between A and B. There exists some number, oh, my spelling's awful, sorry. Some number C in the interval A to B such that the derivative at C is 0. In other words, the slope of the tangent line is 0 somewhere. There's some point in this interval where the slope of the tangent line is 0. All right, so a little bit kind of confusing to think about it like this. Let's take a closer look at some diagrams. Let's take a look at Raleigh's theorem in a couple of different possible diagrams. The first possibility I could have is, again, I have some closed interval from A to B. and I know the value at A and the value at B have to be the same. They have to be the same value. What happens in here? Lots of different things can happen in there. Has to be continuous though. Well, the first thing that could happen would be kind of boring, would be something like this. And just connecting the 2 points here. Now what Raleigh's theorem says is that there's some point in the middle C such that the derivative would be 0. And as you can see, I could pick a whole bunch of different values of C. Right here, the derivative would be 0. Right here, right here, right here, but pretty much any of those points, because it's a horizontal line, because it's a constant, all of the points in there could be different C values where the derivative is equal to 0. Let's take a look at another possibility. And again, in order to set up Raleigh's theorem, we have to have that the starting point, the f of A and f of B are the same, whatever they are. I'm drawing them up here. They could be down here or wherever, as long as they've got the same y value. And of course, I could have something completely different between them. I could have something that looks like this. Well, Raleigh says that there is some value C, and I think we can see where it would be right about here. There would be a value C somewhere between A and B such that the tangent line would be 0. Well, another possibility, let's take a look at another possibility now. Suppose I have two values, an A and a B, and they have the same starting point. And this time I get something that looks like this, and then I get this, and then I get something like this. As long as f of A and f of B, A and B is my interval, and A and B are the same, Raleigh's theorem says that there is some value C where the tangent line would be 0. And I think I can spot a value here. Here is a C value where the tangent line would be 0. I'm going to call that C1 because look, there's another one right here. Call that C2. There's two of them. There's 2 points here. Try it out. To think about it yourself. If I was in class, I would challenge you to pick 2 points, and anywhere, as long as the values are the same. It has to be continuous. Connect those 2 points, and so that try to do it so that there wouldn't be a maximum or minimum, so that there wouldn't be some point where some value C that would have a 0 tangent. I mean, I could do something like this. Again, I think I can see that I'm going to have some value of C, maybe right about here-ish, where I'm going to have a 0 tangent. And that's what Raleigh's theorem is saying. And in Raleigh's theorem, the important restriction is that f of A and f of B have to be the same. The starting points are the same. All right, so now let's look at a sample problem dealing with Raleigh's theorem. What I want to do is I want to verify the 3 hypotheses of Raleigh's theorem and find the C value, or as we saw, there might be more than one C value, that satisfies the conclusion of Raleigh's theorem. All right, verify the 3 hypotheses of Raleigh's theorem and find the value C, at least one value C, that would satisfy the conclusion of Raleigh's theorem of what? All right, so here comes my function. I'm going to give you the function f of x equals x cubed minus 3x squared plus 2x plus 5. And now I need an interval, and I'm going to choose the interval from 0 to 2. So here's my function. Here's the interval. Now, the three hypotheses. First, is this function continuous between 0 and 2? Well, this is a nice, well-behaved polynomial. It's going to be continuous everywhere. So, yep, okay, that it satisfies the first hypothesis. Second, is it differentiable between 0 and 2, the open interval? Well, it's continuous everywhere. It's differentiable everywhere. It'd be easy to find the derivative. And the first thing is, the third part, is f of a equal f of b? Now, that's going to take a little bit of work. We're going to have to think about that. Is f of a equal to f of b? In other words, f of 0, does that equal f of 2? Is the value of the function at 0 the same as the value of the function at 2? So I'm going to have to do a little bit of work here for that third conclusion. So f of 0. So here we go. So let's find f of 0. I'm going to plug 0 in here. So it's going to be 0 cubed minus 3 times 0 squared plus 2 times 0 plus 5. And I don't think there's any difficulty here. I think we can see that that's going to be 5. What is f of 2? F of 2 is going to be 2 cubed minus 3 times 2 squared plus 2 times 2 plus 5. And let's see, I'm going to get 8 here. 2 squared is 4. Minus 12 plus 4 plus 5, and I can see that that is going to equal 5. So, Raleigh's theorem is satisfied. Yes, they're the same. F of 0 is 5, and f of 2 is also 5. So the three conditions of Raleigh's theorem are satisfied. So now what I want to do is find the c value, because Raleigh says that in this interval, this function will have some c value in here, such that the derivative is going to be 0, which we realized from yesterday means it's going to have a maximum or a minimum. Well, how are we going to do that? Let me add a little bit of piece of paper here. I can add some paper over here. So I'm going to, first I'm going to find the derivative. So the derivative of the function I think would be fairly easy to find. The derivative of f of x is 3x squared minus 2 times 3, 6x plus 2. And there has to be a value in here where it equals 0. So I'm going to set this equal to 0. I'm going to change my color here. 0 equals 3x squared minus 6x plus 2. And there has to be a solution that's between 0 and 2. Let's see. We need to solve this. Is this factorable? 3 times 2 is 6. Can I think of two things that multiply together to give me 6? Add up to give me negative 6. Oh dear, that's not factorable. How are we going to solve that? Well, I guess we're stuck with quadratic formula here. All right, so here we go. So we need to solve 0 equals 3x squared minus 6x plus 2. X is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. X is going to equal negative 6 plus or minus the square root of negative 6 squared minus 4 times 3. Oh, I'm running out of room. Times 2. Can we see this? Move it over a little bit here. All over 2 times 3. So x is going to equal 6 plus or minus the square root of 36. Let's see, 4 times 3 is 12, times 2 is 24, minus 24 all over 6. X equals 6 plus or minus the square root of 12 over 6. I'm getting two different solutions here. Let's get the calculator to help us. They're not going to be nice, well-behaved solutions. So let's see, open parentheses. I've got 6 plus the square root of 12 close parentheses, divided by 6 equals, and I'm getting solutions of 1.577, and then the other solution, bring up my previous entry and change that plus to a minus to find the other solution, is 0.422. All right, so what do these numbers represent? These numbers actually represent, because they are the zeros of the derivative, this is my maximum and minimum points. Notice this was a cubic. The lead coefficient was positive. I know the end behavior. So I know I'm going to have a local max and a local min. And here they are. If the end behavior of the polynomial looks like this, the first value is going to be a local max and a local min. Local max, local min. But Raleighs says that one of them has to be in this interval. Well, that one is not in the interval, is it? But this one, sure enough, it is in the interval. It's between 0 and 2. So that is the C value that satisfies Raleighs theorem. That number right there. All right, so there's Raleighs theorem. Now, when we come back for part 2 of the lesson, we're going to make a more general version of this, the mean value theorem, and we'll do a couple of sample problems and look at some examples as soon as we come back.